All right, we're going to go over a few more notes on section 2.5. So, whoops, see some scribbling on here. So we kind of already looked at a graph. We were given a graph of f, and we drew a graph of f prime and f double prime and made some observations. So summing up what we know about what the first and second derivative tell us about our function. If our function is increasing, then the first derivative would be positive. If the function is decreasing, the first derivative would be negative. What we then observed was that the second derivative tells us about concavity. So if the function itself is concave up, then the second derivative is positive. And if the function itself is concave down, then the second derivative is negative. So let's look at some examples of how we can use this information and apply it to analyzing some functions. So here we have functions of pictures. We don't have any formulas yet. We're still just trying to understand what this looks like, how we analyze functions, what it means for a function to be increasing or decreasing, what would that look like on the graph, so that we really understand what this means. And then in chapter 3, we get to some of the shortcuts of how to compute these things. So you really want to be careful about reading, because one tick mark makes a whole difference. So here we're looking at graphs of functions f, g, and h. We want to make sure we're looking at the right function. And then they're going to ask us about the first derivative, the second derivative, or perhaps the value of the function. We don't need to find an exact value. The goal is just to figure out if it's positive, negative, or zero. So we'll just do a few to get a sample. And then if you want to do more practice, this is posted in Canvas as well as the solutions. So f prime at 1 means I look at the graph called f, and I'm going to where x is 1. So I'm right there, the blue dot on the graph. And the first derivative tells me about the instantaneous rate of change. I'm looking for the slope of the tangent line there, if that function is increasing or decreasing. That function is increasing at 1, so the first derivative should be positive. Now the second derivative tells me about concavity. So this graph looks like it's concave down all the way almost until the x-axis. Then it seems to turn around and be concave up. This, of course, leads us to a next question we might be thinking is, how to identify exactly that point where it switches from concave down to concave up? It seems like I'm kind of halfway in between where it turns around to go down and turns around to go up, but we're certainly going to need to develop some more tools to find that point exactly. But for now, I'm kind of estimating it looks like it's right around where that graph crosses the x-axis, that it's turning from concave down to concave up. So certainly when I'm staring at that blue point again, where x is equal to 1, that graph is concave down. If the graph is concave down, the second derivative would be negative. For parts C, D, E, and F, I'm still continuing to look at the function f. If we look at the point 2, for example, my function is now decreasing. So the first derivative would be negative. Sorry, I'm looking at 2, where x is 2 up here. And it looks like I'm still in that area that I highlighted in yellow. The graph is still concave down, so the second derivative would also be negative. If I go over to where x is 5, this graph is now increasing, so the first derivative is positive, but I'm now in an area where the graph is also concave up, so the second derivative would also be positive. In functions g and h, they're both linear. So we already discussed that the derivative or rate of change of a linear function would be constant and equal to the slope. So everywhere on function g, I'd have the same derivative that would be equal to the slope of that line. That line is decreasing, so certainly the slope would be negative. So specifically at g of 3, the derivative is going to be negative. Since this is a linear function, there's no concavity. It is not concave up or down, so the second derivative should be 0. H is also a linear function, but h is a constant function, meaning that the output stays the same all the time, giving me a horizontal line. So not only is the derivative constant equal to the slope, but it will specifically be 0. And then again, it also doesn't have a concavity, so the second derivative will be 0. For parts k and l, I'm looking at the value of function f at 1. And they just want me to see if it's positive or negative. So when x is 1, function f is above the x-axis, so that would have a positive value. And for function h at 1, this function is below the x-axis, so it would have a negative value. So if we apply this to an actual problem, let's say we put some context here. Let's say our graph is talking about speed. Here we have time versus feet. So that the rate of change would be velocity, feet per second. So the question is, when is this derivative going to be positive? In other words, when is there a positive velocity? We keep moving forward. Well, this graph is increasing all the time. As time goes by, I keep moving forward. I keep increasing my feet. So since this graph is increasing all the time, the derivative will be positive for all t. So that means that I am always increasing my feet. I'm always increasing my distance. So s is always increasing. It doesn't say I'm always increasing the speed. I'm always increasing my distance. So s is always increasing. Now it's going to ask us about concavity. I noticed that until 2 seconds, this seems to be concave up. And then from 2 to 5 seconds, it looks concave down. That's because from 0 to 2 seconds, the velocity, the rate at which feet change per second, is getting faster and faster and faster. And after 2, it looks like I'm slowing down. I'm still moving forward. The feet that I'm traveling is still increasing, but my velocity is decreasing. So that's what they're asking here for the second derivative. So my second derivative is going to be negative when t was between 0 and 2. That's this part here. Sorry, that should be positive. That's what happens when I try and memorize the graph. So the second derivative should be positive when t is between 0 and 2. That's this part in green where my graph is concave up. And then from 2 to 5, where the graph was concave down, the second derivative would be negative. And then when they say interpret that, this means that my speed or velocity is increasing. I'm actually going faster and faster and faster. And this means my speed or velocity is decreasing. I'm going slower and slower and slower. And just kind of a review, the rate of change of velocity. So if I let velocity, let's call that v of t as a function, then the rate of change of velocity is what we call acceleration. And we'll talk a little bit more about that in class as well. So the other thing we're going to do is try and put these ideas together to draw our own curves if we're given information about the function, the first derivative, and maybe the second derivative. So here, the fact they want a function that's always increasing. That means the first derivative would be positive. The function itself is bigger than 0. That means that I live only above the x-axis. And then it tells me that f prime is increasing. If f prime is increasing, that means f double prime is positive, which means my function itself is concave up. So I need a function concave up, increasing, that lives above the x-axis. So one possibility would be this. And the second one, again, my function only lives above the x-axis because they tell me that the function values are all positive. But now my function is decreasing, so the first derivative would be negative, and the second derivative is positive, so it's still concave up. So it lives above the x-axis, concave up, but decreasing, so that could look something like this. Tomorrow we're going to do a bunch more examples where we have to do these sketches and kind of put everything together. And then we'll talk a little bit more about what it means to be differentiable in general.